Hello, we have defined the joint CDF. Now we want to define joint probability density function. This is the same extension. This is the extension of the probability density function. So the definition is basically very simple. If you have two random variables, if you have the joint density function here, we calculate the derivative with respect to both x and y. When we had just one single random variable, f(x) of x, you calculate derivative of these with respect to x, and then you get probability density function of x. Now I have two random variables, f(x, y) of x and y, so I do derivation with respect to both of them. And because I have two of them, I don't use these d, I do the partial derivative with respect to x, and then I do the derivative with respect to, let's say, y. Okay, so this is denoted by the joint density of x and y of x and y. So this is just my definition. Now, what we want to do, we want to say that we could define the probability of the random pair x and y being any arbitrary area. You remember that I say, okay, if I have any arbitrary area D, I want to calculate probability of random pair being in this area. So in the first example, I claim that this probability of being in this area is defined by this integral. Or another example is that if this area D is simply an area of, let's say, x, this point is x, if it is like that, and this is y, if it is on the right side of this line and this one, which is this probability, can be calculated. So this second example is trivial. The first one we want to justify it. And if you want to find the marginal density functions, you have to get the joint density function and integrate it with respect to the variable you want to eliminate. Similarly, you can get the marginal density for y. You have to integrate with respect to x. So you see that for the density function you need integration, but for the marginal CDFs, if you have the joint CDF, you replace the other one just by infinity, which is easier in the CDF domain. Let's have one example before we make the concept a bit deeper. So the first example is a bivariate normal distribution. That means that we have two random variables which are defined to be jointly normal. The definition of normal distribution, we will have more elegant and better definitions in future. So we'll have several definitions, and each time the definition will become a bit better. So this definition is coming from nowhere, but the future one is more rational. So we call a bivariate x and y to be a bivariate normal distribution if the joint PDF is given by this expression, which is a very long expression. We don't have any justification. We'll have it for future. This guy is a constant, which makes the double integral of these, because the double integral of the joint PDF should be integral of f(x,y) of x and y over any area is equal to probability of random pair pxy being inside D. Okay, now if the D is the whole area, if D is equal to R2, which is to say this integral should be from minus infinity to plus infinity and minus infinity to plus infinity, these probability shall be equal to 1 for D equal that. Okay, so this integral, I forgot to put this dx, dy. So this integral should be equal to 1 when D is R2. So to satisfy this condition, this constant should be there. Now you see that e to the power of something. So if I take log of the joint this function, you will see that ln of the joint PDF fxy of x and y becomes ln of this constant. Let's say this constant is k, so I get ln of k, and then minus, I get this term here, minus 1 over 2, 1 minus rho 2 xy, and then times bracket x minus mu x to the power of 2 divided by this, and blah blah blah. So what you see, the logarithm of the PDF is constant plus a second order polynomial of x and y. Except x and y, everything else is a constant number. So what I could say is that bivariate normal distribution is a distribution which its logarithm is a second order polynomial. Okay. So rho is the correlation coefficient, which shall be always smaller than 1. We'll prove that in future. And we denote the random pair. We say that it has a normal distribution with mean mu x, mean mu y, a standard deviation x, a standard deviation for y, and correlation coefficient. So because we have these parameters, so this is an abbreviation for this big function. So for this distribution, you could easily conclude that the individual random variable should have a normal distribution. So this means that f x of x is equal to e to the power of minus 1 over 2 sigma 2x times x minus mu x to the power of 2 divided by square root of 2 pi sigma 2x. And you write the same distribution for fy of y. So it is very easy, because if you integrate it with respect to x from minus infinity to plus infinity, some of those terms disappear. So